Okay, in this video, we're going to do an example of taking a double integral over a general region. So the problem is written sloppily here. Our function is f of x equals xy, and D is the region enclosed by the graphs of y equals x squared and y equals 3x. So I usually start by trying to get a picture of the region, right? So I've got the xy plane here. I just want to sketch graphs of the functions. So we know y equals x squared. So I'll just sketch, well, that's terrible. Let's do that again. So y equals x squared. Right, should look something like this. And then y equals 3x is going to be a line with a relatively steep slope. And so the region enclosed, right, should be this little slice here. Okay, so we need to find out, let's find out the intersection points. It's worth doing the algebra in case it's been a while. So we just want to find where these two functions are equal. We can factor in x, we get x minus 3, which gives us two solutions, x is 0 or x is 3. So it's easy enough to plot these points. Okay, so now we can go ahead and use our rule, right? If we want to integrate over the region D, we can think of this as going from what are our bounds on x and what are our bounds on y in terms of functions of x. Right? And so looking at this picture, I see x is going from 0 to 3. And y is bound below by x squared and above by 3x. Right? And then we have the function xy, dy, dx. Okay? So now I'm going to just do the inner integral, right? You can do this off to the side. That's what I did in the last video. This time I'm going to do it in here, and I'm going to keep the integral sign for the dx integral just sort of as a placeholder for now, or just like a parentheses or something, right? It's encapsulating all this, and all this work is happening inside. So I have to take an antiderivative of y, and that's going to be 1/2 y squared. X is a constant, so we're going to get x over 2 y squared evaluated from x squared to 3x. And then we still have dx. All right, and then we'll do, again, this evaluation is going to look like, well, we're going to get x over 2 times 3x squared minus x over 2 times x squared squared dx. All right, and so now we're just looking at a function of x evaluated from 0 to 3, right? So before I take the antiderivative, I'll simplify this. I'm going to have 9x squared times x over 2 should be 9/2 x cubed minus, let's see, 1/2 x to the 4th dx. So what do we get? Well, when we evaluate this, it looks like we're going to have 9/8 x to the 4th as our antiderivative here, and we should have one let's see. Oh, sorry, this should be an x to the 5th. That's where my mistake came in. Pardon me. All right, we had x to the 4th from the x squared squared, but there was an extra factor of x here. So this looks like 1/12 x to the 6th evaluated from 0 to 3. So we get 9 times 3 to the 4th over 8 minus 3 to the 6th over 12. And then everything else is zeros, and you can work out these fractions, it looks like 243 eighths. Okay. Or what, 30 and 3 eighths, 30.375. I think, yeah, that should make sense. Okay, so first of all, straightforward, I think, right? The big work came in figuring out the region D and then just following the program, right? This idea that we can take the bounds of Y to be given by these functions of X. However, I want to do something different with this now. Notice I could look at this region in a slightly different way. I thought of this as the function y equals x squared, and this as the function y equals 3x. But there's nothing stopping me from thinking of this as x equals the square root of y, right? In this portion, it's the positive square root of y. Or this as being x equals y over 3. Right? If I look at it this way, right? So in the first case, we described D as the region xy such that 0 is less than x. So x is between 0 and 3, and y was between x squared and 3x. But I can equivalently describe the region D as the points where y is between 0 and 9, and x is between y over 3 and the square root of y, right? That the x values begin on this line and end when they hit this line, right? The low end to the high end, right? Up here, there's a smaller interval, right? So in the first way, we were bounding y, saying what's the highest to the lowest y value in this direction. Now I'm bounding x by these functions, and y goes from 0 to 9. So I like to think of these things as spitting out these area functions that we then integrate over the other variable. In other words, the first way, we first found an area function saying for each value of x, what's the area of slicing that area in the x direction, right? Like this, like a vertical slice here. And then adding up as we move across all the x. Now we're going to find an area, the sort of horizontally sliced areas, and then we have to go through for each value of y, and then we add up them all up. So we should expect to get the same result. There's nothing wrong with how I described the region D here, right? There was these type 1 and type 2 regions. It's just which direction are we looking, but there's nothing special about either direction. So in this direction, y is going from 0 to 9. X is going from, what did I say, y over 3 to the square root of y. Our function is still xy, and now I'm doing dx dy. So first, I'm integrating over x between these two functions, and then I'll integrate over y. Okay? So same sort of process, right? I need to take an antiderivative of x, which is 1/2 x squared. I've got y as a constant, and I'm evaluating it from y over 3 to, let's change this to rational exponent, dy, right? Again, now the integral sign at the beginning and the dy at the end are just bounding this thing. They're just containing it for the moment. So all the work's happening on the interior. 0 to 9, I'll get y over 2 times y to the 1/2 squared minus y over 3 squared dy. Now we've got an integral just in y. Let's do some cleaning up. I've still got y over 2. Y to the 1/2 squared gives me y. Here I get y squared over 3 dy. Let's clean up just a little more. I get 1/2 y squared minus 1/6 y cubed dy. And then I can take my antiderivative. So what do I get? 1/6 y cubed minus, let's see. Oh, I missed something. This, pardon me, this should be a 9, this 3. I keep making little errors in there. My brain's alerting me without telling me precisely what it is. So that makes this an 18. Sorry about that. So then we get 1 over 72 y to the 4th. All right, that's our antiderivative. Evaluating from 0 to 9, I'm going to get 9 cubed over 6 minus 9 to the 4th over 72. And if you work that out as expected, oh yeah, that's what I have. Sorry, I'm just looking at my notes to make sure we did this all correctly. And I'll let you slog through those fractions, but we do get precisely the same fraction. Okay? So the point of this, A, was just to give an example of how we do these kinds of integrals, but also to note that sometimes we can do them in either direction. Sometimes, in this case, they were pretty equivalent. There wasn't a huge difference in doing one or the other. Sometimes there will be, though, and I'll do an example in the next video where we'll see that changing the order of integration makes it go from an integral that can only be solved, or at least one of the solutions. There's no simple solutions to the antiderivative. You'd have to defer to infinite series. When you do it the other way, it's a pretty straightforward. The trickiest integration technique you have to use is U substitution. So it can often behoove us to note what happens when we look in the other direction. And they should give the same result regardless. Okay, that is going to do it for this one. Thanks, everybody.